So I'm going to talk about the effect of climate change on load and how much that's increasing costs. And basically this analysis started when summer of 2023, it was extremely hot. I opened my electric bill and it was just like, holy crap. I mean, and so I immediately go and I turn the thermostat up. And then probably half an hour later, my kids walk out of their rooms. They turn the thermostat down. So we had a big fight over a thermostat. And it occurred to me, this is, for me, it's an inconvenience. I don't like paying the money. But for the poorest in our society, this is an enormous problem. So I wanted to quantify how much climate change is actually costing people. So the first thing you want to do if you want to do this calculation is you need to estimate how much demand there is as a function of temperature. And so I'm going to show you a plot here of daily average temperature from ERA 5 and ERCOT, which runs the Texas grid. So ERCOT's the Electric Reliability Council of Texas. They run the Texas grid. They provide data. And so I'm going to show you 2023 data, and that's what it looks like. So each dot is a day in 2023. The orange line is a sophisticated machine learning. No, I'm joking. I wish I had a machine learning. It's a fourth order polynomial fit, and I put a categorical variable in to handle weekends and holidays. And so I can predict, given the Texas average temperature, I can predict the demand with an average error of 0 and an RMS error of about 1.3 gigawatts. So it's actually an incredibly good fit. If you tell me the temperature, I can tell you the demand. Now, what this means then is I can do the following. I can take the temperature from any day, any year, so I have 2000 in the upper left corner, and I can plug that into the fit. And I can tell you what the demand in 2023 would have been if we'd had the temperatures from a different year. And so let me just say it again, because people always get confused about this. We're simulating 2023 demand. So the population of 2023, the infrastructure of 2023, the amount of electrification of 2023, everything's 2023 except the temperature. So now what I can do is I can take the temperature going back to 1950, I'm using ERA 5, and you can see this is I should say the temperatures are population weighted. And so I'm taking the temperatures and I can plug this into the polynomial and I can say what would the temperature what would the demand have been in 2023 if we had had the temperature from any of these other years. And that's what this plot shows. So the average demand in 2023 is about 50 gigawatts. I was looking at other demands like New York's like 30 gigawatts. It's very cute to see these other states. Texas, it has an enormous power demand because of cooling and industry. And so again, this is the demand that would have occurred in 2023 with the weather year. You see this is weather year. So if you take the temperatures from any of these years, you can predict the demand. So now we want to say, we want to ask the question, what's the impact of climate change? So to figure this out, we're going to take a baseline period, which is 1950 to 1980, so the middle of the 20th century. You know, ideally you'd want to do pre-industrial, but we're not going to do that. We're going to do middle of the 20th century. And then we're going to compare that to the 10 years, 2014 to 2023. So it's almost the last 10 years, not quite. And the difference between these two is climate change, or is how we're going to define climate change. There are different ways you could have done it. This is the way I did it. And if you actually look at this, and you say, how much did climate change increase demand? It was about 0.9 gigawatts, about 1.9%. Now, when I first looked at it, I thought, that's not very much. And you sort of think about it, you think, okay, well, increased demand, 1.9%, so prices go up 1.9%. And then I thought, but my bill went up a lot more than 1.9%. And so I started thinking about it. It turns out this is only the first half of the problem. And the second half of the problem is actually much bigger. And it's not just that climate change increases demand, but as demand changes, the price changes. That's how the ERCOT market operates. So let's talk about that for a second. So I'm going to show you a plot here. The x-axis is ERCOT daily average demand, so the same thing I plotted earlier. And this is the wholesale price. So ERCOT sells power on a wholesale market. The price changes every day. In fact, it changes over the state, but I'm not worrying about that. I'm just averaging it over the whole state. And this is what it looks like. And you can see there's also a piecewise linear fit to it. And so there are two things to note on this. First of all, at all levels of demand, if the demand increases, the price increases. And the reason is because as the demand increases, ERCOT has to pull progressively more expensive power into the energy mix. And ERCOT charges the most expensive power. They have what's called marginal pricing, which means the last unit that gets pulled on, that's the price everybody pays. And so if when demand's really high, you're pulling extremely expensive coal-fired power onto the grid, or peaker plants, which are very expensive, and that's what everyone pays. Now, the other thing you'll notice is that there are really two regimes on here. There's this regime right here, which I'll call sort of the normal regime, and that's what's happening as I described it. As demand increases, ERCOT's pulling more expensive, mainly gas generators, and then coal, and then peaker plants. And then you see this right here. And what's happening here is at some point, ERCOT says, we are reaching capacity. And you do not want to reach capacity on electrical grid. So they say, we're going to jack up the price to get people to stop using power. And so you're seeing grid constraints. So this is basically the physical constraint of the grid, the generators, and more importantly, the transmission lines. Transmission lines have capacities. You can't push more watts through a transmission line than it can hold. Okay, so this allows us to do the following. We're going to take the temperature in any year, and we're going to plug it into our fourth order polynomial. That's going to allow us to predict the demand in that year. Now, once we know the demand in the year, we can use the orange lines in here to predict what the price is. And then once we know the price and the demand, we multiply them, and we get the total cost on that day. We do this for every day from 1950 to the end of 2023. And then we can aggregate those, and we come up with the amount for any month or any year that you're paying. I should say this is for the wholesale market. I'm not going to go into all the great details, but you can ask me about that if you want to know details. Okay, so here's what it shows us. So again, this is the change in cost of electricity due to climate change relative to the mid-20th century. So if you see January, we paid less money, $124 million less. That's 12% reduction in total wholesale cost. And that's because winters are warmer, so people are running their heaters less. Summer, on the other hand, we're spending $800 million more in summer 2023 in the recent period because of climate change. 44% increase, and that's again because people need to crank up their air conditioner. And that looks a lot more like what my electricity bill was doing. And if you aggregate that over the whole year, you see a large overall net increase in cost. So this is, and it actually works out to $80 a person. So for every Texas resident, that's $80. That is a lot of money, and a lot of people cannot afford that. If you make them pay an extra $80, they're just not going to run their air conditioner, and they're going to suffer, or they're going to run their air conditioner and not going to have money to do other things like go to school or start a business or do other things. This is an enormous drag on our economy. Now, the thing that's kind of struck me when I looked at this is the demand only increased 2%, but the cost goes up 16%. I thought, that doesn't seem right. So I really thought about this. And what's happening, what I figured out was happening, and I'll show you this in a second, is it's this jump right here. So if you're in a regime where you're at a demand level that's right below the constraint level, and then climate change pushes you over that, where the price starts rising rapidly, that's really where you get hammered. That's what drives the cost up very much. It's this constraint on the grid and climate change pushing you into the constrained regime. Now, so we can test that by running a second case where I just extend this normal regime out. So I don't have a constrained regime. The price continues to smoothly increase at about 90 cents a gigawatt. And if you do that and you say, well, what's the price increase here? You see that it doesn't change the winter very much, because winter you're not really in the constrained regime very much. Winter Storm Uri aside. August, though, you can see you see much less of a price increase in August. And again, that's because in August last year, the average wholesale price was $300 a megawatt, which is really expensive. And we were basically living in the constrained regime in August, or 2023, not last year. And the annual is about a third. So this constrained regime is really what's driving up the cost. And that's why, even though the demand only went up 2%, because of the way ERCOT charges, and because of the way when the grid starts getting constrained, the price gets jacked up, there's an enormous increase in cost. Let me conclude. Climate change is costing us money, so it's not a future problem. Newsflash, it's happening now. All of us are paying a climate tax because of this. Now, it depends on, I will say, it depends on where you live. I imagine if we did North Dakota, they might save more money in the winter, but certainly not in Texas. In Texas, any money saved in the winter is offset by much more demand in the summer. I realize this is a typo. It should say 2023 saw demand increase by 0.9 gigawatts entirely due to climate change. I didn't notice that until right before my talk, and I couldn't change it. The price of the increased wholesale cost of electricity by $2.1 billion, and that's about $80 a person. And this could be drastically lowered if we were able to eliminate constraints in the grid. So a lot of this comes from the policy. It's not physics, it's the policy of how the market actually operates. I'd like to thank NSF for support, and you can get a preprint if you're interested. Thank you.